we are now with the third talk of the day, the second day. And this time we have more about the q-binomial identities that we heard before. This time we have Álvaro Gutiérrez all the way from University of Bristol, keeping with our worldwide audience and speakers. Please do go on.
Thank you very much for the presentation, also for the invitation. I also want to thank. So I had some help to set up this technical side of things from Sergio. So I have to skew by so they can see his name, and that's him. All right, so I want to begin with a meta theorem, which is that every combinatorial formula has a q-analogue. And we can prove this meta theorem because a meta theorem is usually proven by abundance of examples. So let's see some examples. Here is the binomial theorem, and it has a q-analogue. It's certainly a combinatorial formula. And here you see you have something to the power of n, and I can change that for a product of n things that look all very similar to the original thing, but I have a power of q. On the other side, I had a binomial, and now I just put a q-binomial. All right, let's look at another example. So this says that the number of dict paths of a given length is counted by the Catalan number. And this has a q-analogue. We have seen this in a previous talk, where you are counting these dict paths according to some statistic. So this is like an averaged majorizing index. And we have this other formula here. This is Stanley's hook content formula, which says that the number of semi-standard Young tableau is counted by this product in which you range over all cells of your Young diagram. And you have here n plus the content of this cell and the hook length divided by the hook length of the cell. And this has a q-analogue. On the left-hand side, you change this for a certain specialization of Schur polynomial. And on the right-hand side, you just put brackets everywhere. All right, so there is even this field of hypergeometric functions in which you come up with basically a continuum or an infinite amount of q-analogues of formulas. Yeah, every combinatorial formula has a q-analogue. And this is horrible. This is horrible for us. Now, of course, I'm only saying this because I want to be a bit controversial. I want to draw your attention. But there is a sense in which I actually mean this statement, and I want to try to convey why. But before that, let me set up some ground definitions. I'm going to be working with quantum integers and quantum binomials. So I think before we were looking in the other talks, we were looking at more combinatorial ways of defining q integers and q binomials. And I'm instead going to use this centered version. So these are not polynomials, but rather Laurent polynomials. If you like the other ones, then in every single formula that I present today, you will have to figure out what powers of q to add, but then the rest would be the same. And the main problem I'm interested in is the following, is the problem of SL2 plethysm, which says, so you take this q binomial and you can express it as a linear combination of q quantum integers. And there are some coefficients in this combination. These coefficients are non-negative. And the question is, what are these coefficients? How do you compute them, or what do they count? All right. And the name SL2 plethysm, of course, doesn't come from this version of the problem. It comes from representation theory. And let me introduce it to you. I just need very basic facts about SL2, which is the 2x2 matrices over C with trace 0. And I'm looking at it as a Lie algebra. So it has a Lie bracket, but this is not really that important now. These facts are the important part. The first thing is that if I have a vector space in which SL2 is acting, that's a representation of SL2, then I can take the symmetric power of this vector space, and I still have a representation. The next fact is that the irreducible representations are constructed exactly in this way. So 2 by 2 matrices act on C squared naturally, and then I can take the symmetric power of that, and those are the irreducible representations, which have this name, irreducible, because any other representation can be reduced, can be expressed as a direct sum of the irreducible ones. All right, with these three facts, I can propose this problem, which is to decompose sim n, sim m, c squared. So, sorry, here we were. So here what I'm doing is I'm taking c squared and sim m of c squared, so that's an irreducible. And then I'm applying fact 1 to take the n symmetric power of all of that. And now this whole thing, it's itself a representation by fact 1. By fact 3, it will have a decomposition into irreducibles. And this decomposition will look something like this. So each irreducible will appear some number of times. And these numbers are the same ones as I had before. And here we have an equivalence between these two problems. So I'm not saying anything deep when I interpret this representation theoretic statement as a q-binomial identity, or vice versa. If I start with a q-binomial identity, I will always find such a q-binomial identity, I will always find a representation theoretic counterpart. So now, why did I say that the abundance of q-analogues is a bad thing? Well, you see, in this problem, the ingredients are quantum binomials and quantum integers, and that's it, right? And of course, binomials and integers appear in all combinatorial formulas, and hence q-binomials and q-integers will appear in all q-analogues of these formulas. So when you try to study this problem, the first thing that you do is, let me go to the literature and find some formula that I can use to try to inform this decomposition. And you find that there are so many formulas. There is an infinity of such formulas because every combinatorial formula has a q-analog. But not every combinatorial formula will help you understand this decomposition. And so the question that we want to ask is, which ones do? So which Q identities reflect deeper properties of these plethysms? All right? I hope that's the question that I'm posing is clear now. And I want to begin by showing you an example of an identity that I do think reflects a deeper property of plethysm, which is this one. It's the Tiemann leader identity. So on the left and the right-hand side, I have two ways of counting the number of ways of forming a government. So on the left-hand side, you start with n plus m plus d citizens, and you choose the lawmakers, n plus m lawmakers from those. And then from the lawmakers, you choose those that are going to become ministers. Right? On the right-hand side, I start with the citizens, and I choose from those the lawmakers that are not going to be ministers. And then from the remaining population, I choose the ministers. And so both of them just count all of the possible governments to form, and hence this is an equality. This is a combinatorial formula, so it has a q-analog, which is this one. I just switch every parenthesis with a bracket. And q-binomial formulas have an equivalent statement in terms of representations of SL2 over C. So I get this isomorphism of representations. Now, so far I haven't done anything. Here I have applied my meta theorem, and here I have an equivalence. To go from this isomorphism down, what I'm doing is I'm taking characters, and the other way, this is called a categorification, because I'm starting with a ring and I am ending with elements of a category. But I have not done anything. Now, why do I say that this is an example of a q-binomial identity that maybe says something deeper? The reason is because I can lift this one step further up to an isomorphism of representations that holds over all fields simultaneously. So there is a map that goes from here to here, and there is an isomorphism for all f simultaneously. And of course, if I take f to be c, then I recover what I had before. But here I am saying something deeper. This is something new. Okay, now there are some weird symbols here. I have sim lower m, sim upper n, and stuff like this. So I want to unravel what I mean by those symbols. And it's because there are two ways of defining asymmetric power, usually, of a vector space. The first way is to take, so sim lower n, is to take the nth tensor power of your vector space, and then take invariants under the action of Sn that just permutes these tensor factors. So if you write it out, it's the expressions that are invariant by this action. And this is a subspace of the tensor power. I could also start with the tensor power and quotient it in such a way that I obtain sim upper nv. And this quotient looks like this. I take the nth tensor power and I quotient by all the expressions of this form. So this basically says that in the representatives, I will be able to swap contiguous elements. And so this product becomes symmetric in this quotient. All right. Now, usually you don't distinguish between these two constructions. And the reason is because over C, they are isomorphic. They are the same functor. But they are not the same over all fields. So there are very elementary examples in which n is, I think, 2 already, and these two things are not the same over some field. And so we really need to distinguish. And this complicates things, but also makes them a bit stiffer. So you don't have as many freedoms of choice. So you cannot nilly-willy choose either the lower symmetric interpretation or the upper symmetric interpretation. Because, for instance, there is this result of Owen McDowell and Mark Wildon, which says that, well, this is lifting this identity, which says that the q-binomial is symmetric in M and N in this way. And you can lift this all the way up to the generality that we saw before in this manner. So sim lower m, sim upper n f squared is isomorphic to sim upper n, sim lower m f squared. But the theorem says even more. It says that if you start swapping here these dualities, so these two things are dual. If you start swapping these dualities, you're not going to find any other pair of representations with these characters that are isomorphic. So this is the only choice. You don't have any other choice. Okay? So distinguishing between these two things or going to the generality of F makes you be more careful about what you're doing. Now let me demystify the definitions a bit more even. So we are going to be talking about this symmetric power of S squared. And this is by the definition of the upper symmetric power. This is just taking, well, F squared, I'm going to give it a basis, X and Y. And this is just the polynomials in X and Y whose degree, they have homogeneous degree D, right? Okay, so these are polynomials over F. Now note that if I know who D is, then I can de-homogenize. So I can set Y equals to 1, and I don't lose any information, right? Because I always know how to homogenize back. So this becomes isomorphic to this space. And this space I'm going to denote by this symbol. So these are polynomials over polynomials on the variable x with coefficients in f, in which the degree of x is bounded above by d. Okay. And what we had before in the theorems that I showed before is a lot of objects of this type. So you have sim lower n, sim upper d of s squared. Now let me take this guy. It's just that guy. Oh no, sorry, that's not what I'm doing here. Let me just apply the definition of the lower symmetric power. So this takes the vector space, raises to the nth tensor power, and then takes invariance. And now I'm gonna note that this guy is just that guy, and so this is the nth tensor power of a polynomial ring, which is just taking a polynomial ring on more variables. So these are polynomials on the variables x1 up to xn with coefficients in f, and whose degree, the degree of each variable, is bounded above by d. Then I'm taking invariance, and this is just, well, symmetric polynomials with this degree condition. So we have this. And this was, I mean, this is a fairly elementary remark that we have done so far, but this actually was the crux on our project. Since we noticed this isomorphism, we unlocked a lot of techniques and a lot of we started advancing on our results much further, much quicker, because we all love symmetric polynomials, and there are many properties of them. And you can start thinking, for instance, I can give a basis to this space. So this is a basis of this space is given by monomial symmetric polynomials whose indexing partition is contained inside of a given box, or Schur polynomials whose partition is contained in the same box. And now I can do combinatorics on these objects, right? And note that I have now brought symmetric polynomials into representation theory, but I have not taken characters. So this I have not taken a character at any point, and yet I have ended up with symmetric polynomials. Usually, when you take a character, you associate to each representation one symmetric polynomial or one symmetric function, depending on what representation theory you're working on. But here, we are associating to one representation a whole ring or a whole space of symmetric polynomials. It's not a ring. It's a whole space of symmetric polynomials. Okay, so this is something else. All right, so let's go back to this thing that we had before. This is the Tiemann leader identity, and then we have the q-analogue of it, and then we categorified it to some statement that is equivalent in terms of some plethysms of SL2. And then I announced to you that you can lift this over all fields simultaneously. But now I know what to lift this guy to. I lift it to some space of symmetric polynomials. So I lift it to a space of symmetric polynomials in which I have m variables and a degree bound on each variable of n. And I can do the same for all of these. Okay, and I still need to prove this isomorphism. And let's think. On the left-hand side, I have polynomials in 3 families of variables. I have x, y, and z. And you know that I have as many z's as y's. And on the right-hand side, I have 2 sets of variables only. You also note that here the degree of z is bounded by n, and the degree of y is bounded by d, whereas on the right-hand side, the degree of y is bounded by d plus n. So what could possibly be the map? The map is as simple as this. I take a polynomial in 3 families of variables, and the z's, I just map them to the y's. This is a remarkably simple map. And so what I want to convey by showing you what the map is that actually when you go up to this level of generality, you may be simplifying things, not complicating them. I think the proof of this isomorphism would be more complicated if we hadn't realized that when we go up and we are forced to take the choices on dualities in a very fixed way, then it becomes a very easy polynomial map. All right. Now this formula then, I'm going to say it's one of these good formulas because it tells me about plethysm. But if my heuristic is good, then not all formulas should lift. And indeed, I have this property because the Q Pascal identity, for instance, in the center version, it has this power of q to the n and this power of q to the minus m, and I just don't know what to do with them when I go up to all fields simultaneously. And so this doesn't look like it's going to fit this framework really well. And if this one doesn't lift, then, well, since this is the defining relation of q-binomials, then not all q-binomial identities will lift. So this is actually a heuristic that is going to be able to distinguish between formulas, the good ones and the bad ones. Okay, so not all formulas lift. Which ones do lift? And here is a comprehensive list. So the first one is this one. Actually, I have been using this one implicitly this whole time because, so on the left you have Q, you're counting Q subsets. No, sorry. In the left, I'm counting n subsets of a set of cardinality n plus m minus 1 with some Q statistic. And on the right, I'm counting n multi-subsets of a multiset of size m, total size m. So this guy on the right is what is more closely related to the objects that we have been looking at, whereas this guy on the left would be more faithfully represented by some exterior power of a symmetric power. But since there is this isomorphism, I can just use this symbol instead for all formulas. Then we have this one. We have already seen that the symmetric powers, that the q-binomials are symmetric in n and m. This one we have already seen too, because it's the Tiemann leader identity. Next, we have this one. So this one is a bit more complicated because it involves some Schur polynomials there. So where does this identity come from? It comes from Stanley's hook content formula. When you evaluate it in a hook, the right-hand side becomes just a product of two q-binomials. And to lift this right-hand side, we know how to do, but to lift this left-hand side, you need a notion of a Schur functor more generally. And actually, again, dualities do play an important role here. And we don't want Schur functors, we want Weil functors, which are their duals. So here you would have a Weil functor indexed by this partition, plethysm with some symmetric power, and this is isomorphic to the tensor product of two plethysms of the ones we have seen before. Ickenmeyer, Omar, and Tsitsilidas showed that, remember that I want to study the plethysm problem because I want to study these coefficients A. These are the plethysm coefficients. But actually, this for SL2, these coefficients also appear when you study Kronecker representations. And this equality also lifts all the way up to the field-independent setting. Next, we have this identity right here. This is an inequality. And what this means is that if I take the left-hand side minus the right-hand side, this is a non-negative linear combination of quantum integers. This one is still not out. It will be on the archive fairly soon. And finally, this formula here, which you can see is much more complicated. So on the left-hand side, we again have a Schur functor or a Weil functor. On the right-hand side, we are also going to have some Weil functors, but we're going to have a sum of them. And each of them is multiplied by some q-binomial. So they, when you lift this up all the way to field-independent setting, actually what you get is that this sum is not split. So you don't get a direct sum. You get a filtration in which these guys are the layers of the filtration. So this is much more complicated. You can see how if we go back to what was known before we started working, and what was known since we noticed that this isomorphism between plethysms and symmetric polynomials. Then we started proving this, which has more parameters. Then we started introducing Weyl factors, and now we have filtrations. So every time there is some increase in complexity that is non-trivial. And you may also wonder, why did we set up to show these formulas? So like this one, this one, which I didn't say where this one comes from. This comes from the q-Fabchalsus formula together with some Jacobi through the identities. But it's a weird list of formulas to try to prove, right? Like, why did you set up to prove these ones and not other ones? And the reason is because I have secretly been telling you about a categorification project. When, and this is my last slide, when categorification began as a field of algebra, people wanted to categorify quantum groups. So let me explain to you what that means. I have SL2 here, and SL2 can decompose into upper triangular and lower matrices, lower triangular matrices, and diagonal matrices. So you have this decomposition. Then if you don't want to study representation theory of Lie algebras, but you rather want to study representation theory of algebras without the Lie, you can study the universal enveloping algebra of SL2. So it's an algebra with the same representation theory. And this is an algebra presented by these four elements, which correspond to, so this is E, these two correspond to that guy and minus that guy, and F corresponds to this guy. And they will have some relations depending on how these matrices multiply. And again, you can decompose this into, this is called the triangular decomposition. So you have the upper triangular, the diagonal, and the lower triangular part. And then you can put a Q in everything. So you can change the field for something that depends polynomially or in terms of Laurent polynomials on Q. And you have a similar decomposition. And people have tried to categorify quantum SL2, quantum groups, since the beginning of the project of categorification. And we have gotten very close. So we have categorified the ring of representations of UQSL2. That was the first major breakthrough by Stroppel. Then Loda and Kovanov categorified idempotented UQSL2. So that's categorifying almost this guy, except that you see the triangular guys, they changed for an easier version of the diagonal part. But we still don't have a categorification of non-idempotented UQSL2. And there is this program by one of my co-authors, Martínez, which gives you a potential way to go forward. So in this program, you would map each of the generators of this diagonal part to some plethysm of the type that we have been seeing, and then there are some relations that you get out of this, and these are the relations that we are proving one by one, and we are getting closer there. All right, thank you.
Let's thank the speaker. So okay, so we have time for questions and comments. So does anyone have any questions?
Were you seeing everything flipped horizontally? No.
No, but I think your folders on your shelf are flipped.
Okay, well.
And one of the question marks.
No, that's the Spanish question mark. That's not a typo.
Okay, on a more serious note. Yeah, sorry.
I have a quick question about the something that you mentioned, that some things do not lift. Is that like a philosophy or something that you can prove? Does it have anything to do with the difficulty on categorifying or what? When you say there.
It's closer to a philosophy rather than a theorem that you can prove, because you could weaken the concept of this lift until you could make sense of expression like this. But I really don't want to make sense of an expression like this, so I'm not going to make the effort. And yeah, so this is sort of the approach that we're taking. Yeah, Dari has a question.
Yeah, so can you show me the inequality again with the two products? Yeah, why do you have two of them? Isn't that like true for one of them and then you multiply it with the other one?
I think it is not true for one of them.
Ah. Wow.
But
That's
I
a
actually
good
don't know
question.
where this inequality comes from. Like I don't know what the if he has a name. I have not been able to find it.
Okay, and one more. This is probably a philosophy or a vibe, but you seem to be implying somewhat that the possibility of making this work in characteristic P is related to the possibility of doing this in quantum groups. Is there any actual results to this? Some kind of, I don't know, vibe conjectures to this extent?
No, I wouldn't say so. What I would say is that a better way of saying this, or like a more precise way, is that instead of looking at representations of SL2 as a Lie algebra, we are looking at it as we are looking at the Lie group, and then we are seeing it as a group scheme rather than an actual group. And this is why it has to work over all fields, because it's the group scheme. Then you
Okay, but a quantum group is even less of a group than the Lie group.
Sorry, say again?
But a quantum group is even less of a group than a Lie group, right?
Yeah, that's correct. Yes.
Yes, I see. But you're making the isomorphisms more explicit, and that makes them more liftable. So that's probably the thinking. Well, thank you.
Thanks to you for the question.
Okay, does anyone else has any questions, comments about the setup, wonderful setup?
Yeah, questions for the setup should be emailed to Sergio. Yes,
Okay. That's very nice. That's very nice. Thank you. So let's thank the speaker again.